This lecture, we are going to create an 8-bit register. So far, we know how to use this circuit, and we said this circuit acts as a 1-bit memory or a 1-bit register. If S bit is 0, the output hold on to its previous value. If S bit is 1, then whatever is at I would be written on the out 1. So we call it a 1-bit memory. Now I want to add 8 of these blocks alongside each other like this, and I connect their S bit to each other. You see, if we look at their S bit, it is for all the blocks, it is connected to each other, but I bits are separated from each other. So if S is equal to 0 based on exactly what we said previously, you see they are just the copy blocks of each other with their S bit connected to each other and I that we could provide the input. So if S is equal to 0, all the S bits would be equal to 0, and whatever the out one had from its previous state would remember it, and when S bit is equal to 1, then whatever is at the I would be written on the out 1 exactly based on what we said in the previous lecture, right? They are just the same blocks. I just added 8 copies of the blocks and connected the S bits to each other. So we could create an abstraction like this and say I have an 8-bit I or input and one S bit and an 8-bit output. So the way that this register acts is that the S bit is 1 bit. So if S bit is equal to 0, then the changes on the I wouldn't affect the values of the output. If S bit is equal to 1, then whatever we write at the I would be written on the output, and we say we are able to read from the memory or write to it. But it is not enough for us. I want to add 2 more blocks and see the changes of the S bit. I connected the output of the second block. At the logic level, this would be a NOT gate and this is a NAND gate. But what I want to show you is that, as you see, I connected this out wire to the S bit, which is connected to the S bit of all the circuits, and I want to see the voltage level changes of this S bit based on the changes of the inputs. And if you look, I just give the name of in and CLK for these 2 inputs for enable and clock. Nothing special about them. I just named them enable bit and clock bit. Why do we want to know that? Why do we want to see the changes of or the behavior of changing of the S bit based on the manipulation of EN and CLK? Because from S bit onward, we know the behavior of our circuit. So we want to see how this S bit changes based on the combination of EN and CLK. We know that we have 4 different states for 2 inputs, 0, 0, 0, 1, 1, 0, and 1, 1. Our output right now, if S, we want to see the behavior of S bit. So let's say first check when in EN or enable bit is equal to 0. If this is equal to 0, we have 0 on the gates of M2 and M3, and this is enough for the output to change its value to 1. Why? Because 0 causes the M2, which is a PMOS transistor, and I explained previously, causes this transistor to turn on, and this wire, it would act as a short circuit, connecting the VDD to this wire, which happens to be the input of the next block. So this wire would have the value of 1. This 1 is connected to the gates of all the transistors, right? So we have 1 at the gates of all of these 4 transistors. 1 causes PMOSes to turn off, acting as the open circuit, and M3 and M4 turning on because they are NMOS, acting as the short circuit. So this wire would go to the ground through the M3 and M4 path, having the value of 0. So, and from then on, well, we know if S is equal to 0, then the out wires would have its previous value, whatever that is, and the changes in the I wouldn't have any effect on those values. So for these 2 cases, we know that S is equal to 0 because both of them N is equal to 0. Now let's check the third case, which CLK is equal to 0. So if CLK is equal to 0, then we have 0 on the gate of M1 and also M4. M1 would turn on because it is a PMOS. Therefore, this wire would go to VDD through the M1. We have a 1 here. This 1 would show up at the gates of all of these 4 transistors. And again, through the M3 and M4, this wire would go to 0. So for the third case, we still have the 0. You know, at the abstraction, at the logical level, because this is a NAND gate, for all these 3 cases, we would have a 0. But let's check the for case which you know by now that if both of the En and Cl are equal to 1, then we would have 1 at the gates of all of the 4 transistors. M1 and M2 would turn off, M3 and M4 would turn on. This wire would go through to the ground through M3 and M4 path, which acting as the short circuit. So we have 0 here. 0 would show up at the gates of all of these 4 transistors, causing this wire to go to the high or VDD through M1 and M2, which are the only turned on transistors currently. Therefore, S would be on or 1. So if you look, the only time that S bit is 1, which means that the only time that we could write to the to our register, or again, which means that well, the changes in I could appear on the out wires is when both En and Cl are equal to 1. So I could just abstract this circuit and say what we have here. Let me just maximize this and say that I have an 8-bit register. I have an 8-bit input, or I, which each one of the I's, we have one I, one bit I at the all blocks here. I number 0, number 1, number 2, number 3 to number 7, which would be the 8-bit of our register. I'm just abstracting it. I have an 8-bit register, 8-bit I have an 8-bit out, which are the out 1 wires, which we are interested in their behavior. The out 1 would be the output of our register, and I have 2 1-bit En and Cl. And the behavior of this 8-bit register is in this way, that when any one of the En or Cl is equal to 0, then this register would remember its previous value. The changes of the I wouldn't affect the out wire, and we say the register is always remembering its last value when each one of the En or Cl is equal to 0. But when both En and Cl are equal to 1, then whatever we write at the I would appear on the output. So we could just draw a timing diagram for it, and we say, well, if En is equal to 1, and at the levels that, and for example, this is the, now if these are the I values, it's not important if you don't understand what I'm saying. The only time that the I, if this is I, it has a value. The only time that I could be written on the output, imagine that the out was already 0. The only time that I could be written on the out is at this time. At this time, when clock goes to high, then we would have the out to have the input value. So you see, this is out, this is I, this is En, and this is the Cl. This En, the out was already 0, so it just has the 0. When I goes to some value, the out value wouldn't change. You see, it still is 0 because the condition of out changing with the input is when both Cl and En are equal to 1. But here, when the Cl goes to 1 and has the level, has the 1 voltage level, then out we have Cl as 1, En as 1, then out would have the I value, and after that, even when Cl goes to 0, the out would remember its previous value, because in order to change it again, En and Cl, they have to go high again.